All right, so today we're going to talk about continuity of a function. And generally, if you were to ask a student what continuity meant to them, they would think continuous, of course. And in English class, you might get an example like, this goes on forever, something that goes forever. Okay. However, in math class, to be continuous means something a little bit different. So since we're not in English class, we don't want to use that definition. So in math class, essentially, and this is not a very mathematical definition here, but essentially it means that our function has no breaks. Okay, you should be able to draw it over some interval without picking up the pencil. Okay, so for instance, here's a very funky looking graph, which definitely does not qualify as a function, but it is continuous from here to, up to and not including, I guess, an x value of 6. You could draw it without picking up your pencil. There are no breaks from here to here, right? Now this point's not included, but maybe our interval doesn't include 6. Okay, so that's what we mean by continuous. And we're going to talk about continuity for two different types of things today. The first one is continuity over an interval. Okay, it's very similar to how we find the domain of a function, right? So the possible values of x. And the way it's the same is that we want to look for where the function may not exist, where there's a restricted value, and kind of report the opposite. It exists everywhere else, right? So we look for those few restricted values and then say, okay, other than these couple restricted values, it exists everywhere else, right? Kind of report the opposite of those restricted values. So if you remember, there are 3 places where our domain might have restrictions. 3 things that we can't do. 1, division by 0 is undefined, right? So for instance, if I had a function 1 over x minus 1, x cannot equal 1 because we'd have 1 over 0, which is undefined. Okay, so division by 0, values that make our denominator 0 specifically, we have to exclude. Any even numbered root, like square roots or fourth roots. Odd roots are actually okay. There's no restrictions on cube roots and fifth roots, but even numbered roots, let's say if I had the square root of x minus 2, remember that the inside here has to stay greater than or equal to 0, or we get imaginaries, right? So here, if you set x minus 2 greater than or equal to 0 and solved, we'd figure out our domain is that we have to stay greater than or equal to 2, or we get imaginaries. Okay, our last one is logarithms. This can be, a log base, same thing for natural log. The expression inside of a logarithm has to stay greater than 0. It cannot equal 0, it has to stay greater than 0. So if you set x minus 4 greater than 0 and solved for x, we'd figure out x has to be greater than 4. There is our domain restriction. Okay, so let's do a few examples here. Is f of x equals square root of x plus 4 continuous over this interval? So remember that open bracket means not included, but infinitely close to. So from the left, we can get infinitely close to negative 12, but not include negative 12. And on the right, we can go all the way up to and include positive 12. So again, the first thing I want to look for is, does my function have any of these restrictions? And yeah, we've got an even root here. Okay, so even numbered roots, and maybe we should kind of add this in here. The inside value has to be greater than or equal to 0. For logarithms, it has to be greater than 0, that expression inside. Okay, same thing here. So to find our restriction, we're going to take the expression inside of here, x plus 4, and say that has to be greater than or equal to 0. So that is a restriction on even roots. So if you subtract 4 from both sides, we know that x has to be greater than or equal to negative 4, or our function is undefined. Well, if I look at my interval, right, from negative 12, not included, so open dot, all the way to positive 12, included, do we have any values that don't qualify, right? Yeah, we do, right? I mean, it has to be greater than or equal to negative 4, so kind of here and on. So we do have some values here where my function is undefined. So would it be continuous over this interval? no. Okay, let's try our next one. Example 2, is this function continuous over the interval 0 to 8? So again, we really mean kind of open dot here at 0. It's kind of open dot on my number line. I guess that was supposed to be the open dot. Okay, so open dot on my number line to 8, close dot, the closed bracket there. So from 0 to 8, is my function continuous? Well, let's see, does this have any restricted values? Now, if I have a fraction where x is in the denominator here, this cannot equal 0. All right, that's a restriction for division by 0. So I'm not interested in the top, I'm interested in the bottom here. I know that 4x cannot equal 0. So if you divide both sides by 4, kind of treating this like an equal sign, even though it's technically an inequality, we get that x cannot equal 0 itself. So we look at my interval. Okay, so it could be anything else, right? It just can't be 0. Now, they did exclude 0 here. They have that open bracket, right? Meaning there's a hole in my graph and get infinitely close to 0, but not actually equal 0. So is it continuous over this interval? Because they excluded 0, yes, that was my one restricted value. Everything else is fine, and they use the kind of open bracket, meaning open dot, not including the point. Okay, the next part, and this is probably where we're going to get more questions in this section, is continuity at a point. So more often than not, they're going to give us a function that's mostly continuous everywhere. We'll probably see a lot of piecewise functions in this one. But let's look at our conditions for whether or not our function is continuous at a point. Okay, so a function is continuous at a point x equals c if all three, and it has to be all three, of these conditions are met. If any of them are not met, it is not continuous there. The first condition is that our point exists. If I plug c into my function, I get a real value back. It is not undefined there. So c has to exist. The point has to exist. Okay, so aka the point itself exists at c. The second condition is that the limit exists. And here we are talking about the two-sided limit. So how do I show the two-sided limit exists? Just like we learned earlier, we have to show that the right and left one-sided limits are equal. So does the left-sided limit equal the right-sided limit? Remember, that's how we show a two-sided limit exists. They need to be going to the same value. Okay, and then lastly, the value we get for our point and the value we get for our two-sided limit have to be equal. So the answers from kind of 1 and 2 have to be the same. If they are not equal, it is not continuous. Okay, so here is an example. Determine whether the function is continuous or discontinuous, and we have a piecewise function. So just to re-go over how these work, by the way, typically this right-hand bracket is not drawn in. However, the software I use put it in, so you can ignore it if you want. It's basically saying we're graphing this function for values of x less than 1, so to the left of 1, and then we switch to graphing this function for values of x greater than or equal to 1. So first thing I would look at is, are there any domain restrictions for these two functions? Do I have any division by 0, even numbered roots, or logarithms? And that's no to all three. No restricted values for each of them individually. But now what I'm worried about is when I switch from one function to another at 1, are they meeting at the same place, right? So we need to go through and do this mathematically. So 1, let's find if f of c exists. So the point I'm worried about here is when x is 1. So let's find f of 1. Now note, when I plug in 1, we don't use the top function here because we only use that when x is less than 1. But this one is allowed to be x is greater than or equal to 1. So this is the one we need to plug into for our piecewise function. So we get 1 plus 1, which is 2. Okay, it definitely exists, right? We get a value back. So now 2, we need to show that the limit exists there. So we need to show the limit as x goes to 1 of our function, right? And in fact, we really want to show that the left and right-hand limits are equal. So as I approach from the left of our function and the limit, and we can go ahead from the left. This is the function we're going to use. We can go ahead and put that in here. X cubed plus 1. Does that equal, question mark, the limit as x goes to 1 from the right? Right? We're kind of just checking, does the left and right hand side limit, are they equal? That's how we prove the two-sided limit exists. And if we're approaching it from the right, these are the values that we would graph right from 1. So this is the function we would use, x plus 1. So remember, when we're finding a limit, the first thing we can do is just plug in, of course. So here we plug in 1 cubed plus 1, which is 1 plus 1, or 2. And again, we're checking, are these equal? Over here, we plug in 1 as well. We get 1 plus 1, which is 2. So are they equal? Yes. Okay, so the limit exists. Our point exists, the limit exists. And then lastly, we want to check, are these values the same? Right, this is f of c and the limit. Right, sorry, f of c, I wrote x. And the limit as x goes to c. They are equal, passes all of these. So is my function continuous? Yes. We can prove that algebraically here. Passes all of our checks. Now remember, if the point doesn't exist, if the limit doesn't exist, and if they're not equal, any of those three things, we would say it is discontinuous. So I wrote yes, but I probably should have written continuous. All right, let's try a couple more examples here. Okay, another one, determine whether a function is continuous or discontinuous. Same direction, so you don't need to retype those. So let's try this one. So first thing I want to look at is these functions. Do we have any domain restrictions? Are there square roots? No. Division by 0? No. Logarithms? No. So each of these don't have a restricted value. So now what I'm really worried about is at this point where I'm changing from one graph to another. So let's first figure out one, what is f of, and I'm really worried about this point, -2. So is it continuous or discontinuous at this point? So when I plug in -2, again, the one it's allowed to equal ends up being the bottom function here. So we plug in 1 minus -2, which gives us +3. Okay, it exists. 1 is a check mark. 2, we need to show that the limit exists. So we need to show that as I approach -2 from the left, and left of -2, we would be using the function x squared. Does this equal the limit as we approach -2 from the right? And from the right of -2, right, values greater than, we'd use this function, 1 minus x. So essentially we need to plug in -2 in both of them. So we get -2 squared. Will this equal 1 minus -2? Well, -2 squared is 4. And 1 minus -2 is 3. So I wrote equal twice. Are these equal? No. The limit does not exist. So we can stop right there. The point has to exist, the two-sided limit has to exist, and they would have to be equal. Because the limit does not exist, we know this is discontinuous. And eventually when you're taking, say, the AP Calc test, if you're asked to prove this, you would need to show the mathematics that we just did here. Right? Kind of show that's why it does not exist. Okay, so here's one for you to try out. Very similar to the last two. Figure out if this is continuous or discontinuous. Remember to check for domain restrictions first. If there aren't any, then we're really worried about this point. Show that that point exists, that the two-sided limit exists, and that those two values are equal. Okay, we'll definitely go over more questions. If you have a bunch of questions, we'll go over those in class. Please come to class ready with your questions.